So ranking theory for lateral earth pressures provide us a very solid foundation for analyzing lateral stresses, especially in things like retaining structures. However, it has its shortcoming that it is specific to a certain geometry. So ranking basically can model something like this, and there are even modified versions that are able to model the case with an inclined slope. However, what if you have, so and it even is able to model a case with a distributed load. However, what if you have or even some bizarre geometry like that? So then you can't really apply ranking. Yeah, sure, in our day you can always make a finite element simulation of this, but historically that wasn't always an option. And for this purpose, before ranking, much before ranking, there was another way of doing this. It was invented by none other than the famous Coulomb. So Coulomb not only developed the shear strength equation, but also put that into use. For example, so if you have some sort of retaining wall like this, and let's say you have some ground, what Coulomb said or observed was the failures in the failures in the soil behind such a wall in the active case is, so when your wall is moving that way, he observed correctly that you have a wedge of failure developed like this, which is, as we know, in line with ranking. So from ranking, we know that the active failure planes happen at 45 plus phi over 2 orientation. So Coulomb didn't quantify it like that, but he noticed, okay, there is a wedge mechanism here. So if there is a wedge mechanism, what happens is, as this wall moves to the left, the failure happens by this wedge moving along the shear plane. And as you move along this shear plane, you are making shear failure according to Coulomb's strength equation. So here your shear strength is known to Coulomb. So Coulomb knew the shear strength on the plane and knew that there has to be a failure there. So of course, as you have this, you also have to have another shear plane, because the wall is moving horizontally, but the wedge is moving down. So you also need or you also have a shear failure here along the wall interface. Of course, the parameters there are different. So instead of, so he had to define a new set of parameters. Instead of C and phi, I'm not sure if he called them with these particular letters, but cohesion between the wall and the soil, or let's call that adhesion. I didn't want to call it A because we had A in the modified strength envelope, plus normal stress times tangent delta, where delta is another friction angle, not the internal friction angle of the soil, but the friction angle between the wall and the soil. Okay, so now we are able to define everything. So what then? Then he takes a free body diagram of this wedge. So of course you have these geometric parameters. You can have different angles here, like beta, theta, whatever you want to call them. And if you want a slope in the surface alpha, doesn't really matter. The idea will always be the same. And that idea is, if we break down the forces acting on this wedge, we have the weight going down. And then on this plane, what do we have? We have the normal stress. Let me also put some more letters here. So let's say A, B, and C. So here we are going to have a normal stress and a shear stress. So you have a shear stress and a normal stress. But I'm not going to confine what we do with just what we know from the Coulomb. I'm going to modify it as we go along. So for example, let's consider that we know soil mechanics. Coulomb didn't. In Coulomb's time, there was no soil mechanics, but now we have that. So we have to work in terms of effective stresses and treat pore pressure separately. So let's consider this, plus also maybe water pressures. So you can consider water pressure separately. So now I can relate tau to sigma in a much easier fashion. Moreover, I'm going to separate this tau into two pieces. So I'm going to break that into two. One of them is going to be, so my tau is this much. It is C prime plus stress times tangent phi. And by the way, of course, I'm doing a force free body diagram. I wrote these in stresses. Of course, we need to convert them to forces later. So these will be stress times whatever area we have. So it will be related to this BC length and so on. So leave that aside for a moment. So the components here are C prime and here, let's write it here, sigma prime tan phi prime. So let's write it this one, it's better. So I have two pieces of my shear stress. And of course, you can think in terms of times BC times BC, BC, and here as well, BC. But it doesn't work really nicely because stress is changing over the length. So these are all things like kind of like average. So because it is linear relationship between strength and stress, you can do that. You can replace averages because it will be the same everywhere, the same relation everywhere, the same separation of components everywhere along this line, even when you integrate that later. So let's keep that in mind, that these are like averages. Now, here something interesting happens. I have a normal stress term here, and then normal stress times tangent phi here. So if I actually take the resultant of those two components only, then what I'm going to have here is the friction angle. This is simple trigonometry. Tangent phi is opposite over adjacent. So tangent of this angle is this divided by this, which gives you tangent phi. So now that makes things a bit easier to calculate, because otherwise you have an unknown here, the same unknown here. It will just complicate the math. So instead, Coulomb simplified this picture like that. And you have the same thing on the other side as well. But this time it is with C wall times AC, and so this was also vertical. Here is delta, and here is some other force. In any case, we end up with two unknown forces. So here's another force. So we call this the P and R. So P for active force or active thrust on the wall, and R for the reaction under the soil. Now I have two equations, two unknowns. Well, of course, you didn't need this joining. You could just have just these normal stresses. Average normal stresses would also be two unknowns. But average stress kind of sounds weird. Instead, having a resultant force is a bit better. So then the next step is, by the way, of course, we have the pore pressures as well. So I have the pore pressure here and there. I will deal with that later. So right now, just consider this like in the dry case, so that we first understand how the solution works, and then we can add things like that. So I have two unknowns and I have two equations. Two equations from force equilibrium to solve P and R. So that's it. Of course, back in Coulomb's day, Coulomb was relatively early. So back in Coulomb's day, people didn't have fancy scientific calculators. So all these angles and trigonometry was also really a computational burden. So instead of that, Coulomb suggested, or head to tail method for taking resultants. So let's remember what that was. You must have learned it in Physics 1. The head to tail method is that you can take resultant of vectors, forces are vectors, you can take resultant of vectors by adding them head to tail in a scaled drawing. So what he means then is you can draw your weight, which will be the biggest force in there. So here is your weight. And then you can draw your cohesion in the wall. First cohesion in the soil. Let's put it like this. C, what did we call that? BC. So this is weight. CBC. And then we have C wall AC. And then we have two unknown forces. Okay, how are we going to solve this? The forces are unknown, but their directions are known. So you plot the directions. So one of them is kind of in this orientation, and the other appears to be in this orientation. Then the intersection point gives you both forces, because then you can draw this. So this is your R, this is your P. Very neat, very easy way of dealing with these forces. So once again, I wish I had these side by side. Actually, I can have that. Here it is. So you take this orientation, replicate it here. You take this orientation, replicate it here. And then once you figure out the intersection point, you figure out the lengths. So this is parallel to this. and this is parallel to this. And of course, these are also replicating these forces. This is parallel to this. This is this force here, etc. So let's go into the additional bits now, additional details. So this is how you do it. And actually, you might already guess if you have something a bit more complicated, like, for example, how do we deal with surface forces? Well, surface forces are easy because if you have a surface force, then you need to simply add to the solution. So it's another vertical force. So it just is like extra weight because this is just another vertical force that you can add at the end of this weight term. So surcharge, the surface load is easy. What else do we have? Well, we can have water. Now, when we have water, things get a bit tricky because you can have water partly inside this wedge, not the entire, usually your entire wedge isn't underwater. So then what happens? Then, of course, hydrostatic pressures are, or water pressures are going to be hydrostatic if you don't have any flow. So what you are going to have is you have this much water head there. So you are going to have such water pressure distributions. And they will always be normal to these surfaces. Okay, so let's take resultant and add them up. No, don't do that. The reason for not doing that is because there is a much easier way. Now, consider a glass of water, or consider not a glass, but a vase like this, which has one side different from the other. It is an asymmetric cup of water. The water in there is in equilibrium, right? If the water is in equilibrium, it's not going anywhere. So the forces that the sides of the cup are acting on the water, which are equal to the forces or the pressures the water acts on the sides of the cup due to action-reaction principle. So the forces that are on the sides of the cup, their horizontal components and vertical components are in equilibrium separately. So the horizontal components can always cancel out. Horizontal components of all the pressures on the surface of any water container will always cancel out because the water is just sitting there. So you only have vertical components left. And the vertical components are in equilibrium with what? They're in equilibrium with the weight of the water. But weight of not the water in the soil, it is weight of the water in weight of nothing but water in this V-shaped container, as if there is no soil, it's just water. Right, that's familiar. So my water forces are upwards and they have the same weight as this volume of water. So that's familiar because downwards forces I have include the weight. Now upward force is weight of water. Well, if I subtract the weight of this partial volume of water from the full weight, I will be doing this. Here I have unit weight of soil. Here I have saturated unit weight, yes, but when I'm calculating weights, what I'm going to do is, let's call this dry. It might not be dry, but let's call it like that. So it is area sat times gamma sat. So my resulting weight is going to be gamma times area dry plus gamma sat area sat, and my water pressure here will be minus gamma water area sat. So what is this? Gamma submerged times area sat, or also called gamma prime area sat. So this plus gamma A dry, I can call that weight prime then. So the way to deal with water in your wedge, if you are doing a drained analysis, because remember the previous chapter, you can do a drained analysis or undrained analysis. If you are doing a drained analysis, you need to consider effective stresses and power pressures. If you are doing undrained analysis, just everything is saturated, everything is total stresses anyway. But anyway, here my weight is actually W prime plus, if I have a Q here, surcharge, let's call it some sort of surcharge. Now what else? There is one more complication to this. When we were talking about ranking theory, what did we see? In cohesive soils, the soil and wall can separate. It's called a tension crack. And it happens only in active mode because the soil prefers to do this rather than having to carry tension with its particulate structure. So in this picture as well, I'm moving the wall to the side. I'm moving the wall away from the soil. Therefore, I'm applying extension strains to the soil in the horizontal direction. If I'm trying to stretch the soil in the horizontal direction, and if I have cohesion, I can develop tension cracks here as well. So if I develop tension cracks, I'm stretching this entire wedge. So if I'm able to develop a tension crack like this little triangle isn't going to move. It's not going to provide the strength from this length of soil interface. Of course, its weight will not be pressing on my wedge either, but this shear strength contribution from this is greater than what the weight does to destabilize it. So wait, I can do the same, I can draw the same thing here as well. On the other side, I might have tension crack between the wall and the soil. So my wedge becomes a little smaller, but more importantly, remember I had A, B, C points. They aren't at the top of the wedge anymore. They are at the bottom of the cracks. So that effectively reduces these two. So how do we get ZC? Of course, as I said, we are modifying Coulomb's wedge analysis here by things we know after Coulomb. So after Rankine, we know how to do this. And if you remember, it is equate the horizontal active stress to 0. And when you do that without surcharge, so without surcharge, it is going to be 2c over gamma times square root of Ka, something like that. But anyway, don't memorize that because it changes if you have surcharge on the surface. So anyway, this way you have a much more realistic representation of the soil wedge. Now, this looks excellent, but there is one very big missing piece in this puzzle. Let's go back. What's missing here? In this picture, which quantity is missing? I know the ground surface. If I have surcharge, I know that as well. If I have water, I know that. By the way, you might not know the water, but the common practice is to drill holes into such walls. Such gravity walls usually have holes. You might see them in like retaining walls of gardens, the small scale retaining walls, or retaining walls on the roadsides. They are called weep holes. So when you drill weep holes, you are opening this water to the atmosphere. So you are effectively lowering the water level to where you have the lowest deep holes, for example. So somehow you can manipulate the water pressures and you can know them. I can know or determine these C, W, and delta. And by the way, I didn't mention that earlier, but let's also mention that the delta is in the order of, generally in the order of a fraction of the friction angle. And CW is also a fraction of your regular cohesion. So if you know nothing, you can take these, but If you know the interface properties, by all means use that. Actually, I shouldn't say that. I should say it can be up to 1. It can be up to the friction angle. So let's put it that way. So 2/3 to 1 friction angle. Anyway, so somehow we can test for these parameters. We can determine all the parameters as well. I have the wall geometry, I have the wall height, I have the wall angle. Here is my unknown. I don't know what angle my failure plane is. And you might think it should be 45 plus phi over 2. Why not? The problem is, even ranking theory says, if you tilt this surface, then this is not 45 plus phi over 2. It's something else. So because the problem changes, the geometry is different, and your failure planes on this problem no longer are 45 plus phi over 2. Of course, it is beyond the scope of this course. There is the advanced version of ranking theory, which is able to model the Moore circles here and then calculate the angle here as well. But we don't have that, and Coulomb didn't have that either. What Coulomb had was math. Coulomb was a mathematician, so what Coulomb had was math. I like those old times where people were scholars of everything. He is both physician, mathematician, or physicist and mathematician. So here, he notices, I'm looking for the most critical case. So the most critical case is the case where this wedge applies largest force to the wall, because this plane can be anything, and the plane that has least resistance to this failure will be least supported, will give me the least supported wedge, and the least supported wedge will apply the most pressure to the wall. So Coulomb went ahead and solved this, and then said, so this is for this theta. So for, where is theta? And find the one with that gives the maximum active thrust. And by the way, I'm saying active thrust, but of course, if you want to consider the forces acting on the wall, the forces acting on the wall here in this picture, for example, would be this P plus this CWAC plus also some maybe some water pressure if there is any. But anyway, we don't need to. So this will be forces acting on the wall. But in this consideration, in this finding maximum P, maximum force on the wall, this cohesion with the wall or adhesion with the wall is constant. The water surface is constant, or not constant, but they are independent from theta. The only thing that is dependent on theta is P. So it is enough to just maximize P. And you can do this in two different ways. Either do this or solve trigonometrically parametrically, then you can do this. If you want something to be maximized, then you take the derivative and equate it to 0. So if you solve this instead of this head-to-tail method, if you solve this from two equations, two unknowns, then you can do this, but it is horribly long and gives huge equations. You can find those in the books, by the way. So if you want, you can use those. But of course, in the end, for small surface slopes, you can still consider theta to be close to phi over 2, 45 plus phi over 2. Actually, if you have a horizontal surface, it will be exactly 45 plus phi over 2. Now, you could do the same thing for passive case, because I can go ahead and put my wall, and this time move my wall inwards to the soil. Then what I have is going to be this. And this time the forces, the direction of the forces will be reversed, because this is going up like that. And now I have my cohesion here, my reaction here, and here as well I have my cohesion here, my passive force here. So that's perfectly doable. Except later it was found that that doesn't work well, especially when people started to do computer simulations of proper computer simulations of this. It doesn't work all that well, because yeah, computer simulations work very well with active case. They show you can actually see the wedge happening in those, but here you don't see this passive wedge. The reason for that is because your passive force in the wall is downwards, and it is pressing directly towards the failure surface. So what really happens there is, what in reality happens is, you get some failure surface like this that is actually more critical than this line. It's counterintuitive, because now you are moving even more soil, but this time for passive, P min is the solution. And here, when you have your surface like that, you are pressing towards the surface, so you can generate greater passive resistance here. But if you gently swoop this force down through the curve and up through this spiral, then that is the that is the correct solution. Okay, so we are off. Not only off, but usually passive is a term of resistance. So here you overestimate resistance of something, which is not good. So Coulomb wedge. So Coulomb wedge analysis is not good for passive solutions. So don't use it for passive solutions. For passive solutions, go ahead and use Rankine. Actually, unless you have a really bizarre geometry that you cannot approximately model. So even this one, yeah, it is almost horizontal or something like that. But if you have a bizarre geometry, then you might use the active Coulomb wedge. But having the idea of this mechanism also is useful for thinking as an engineer. So otherwise, in our day, everybody would do computer simulations of this, or just use Rankine if applicable. So it has too many moving parts, so it can be complicated, but you will get a hang of it after solving for a couple of examples.